So first of all, thank you all for being here, and thanks to the organizers for putting together such a nice school. I've had a lot of fun already. And I was tasked to talk about data analysis in large-scale structure, which is a big topic, of course. So I tried to break it down into a few logical steps. That is 4 different units. Overall, my story will be how to go from pixels to parameters. And to do so with large-scale structure, of course, we first should get a bit more of a practical understanding of what galaxies are and how we do galaxy surveys. So if you take one thing away from this class, then that galaxies are not just point particles. They actually have rich astrophysics. And as we push to the next generation of surveys, we really need to understand some of that astrophysics to get the best cosmology out of large surveys. So today I will tell you some about the astronomy and astrophysics of galaxies and connect that to theoretical modeling of halo formation. And then the next steps are to then go from pixels to power spectra. So first of all, how do we build catalogs of galaxies that people can then readily use? And how do we estimate summary statistics from there? And that will basically be systematics. The next step then is to go from power spectra or other summary statistics to parameters. So at that point, we will talk about covariances, different SS inference methods, and what does it take to trust error bars in the end. And then in the final lecture, I will go beyond large-scale structure in the sense of galaxy clustering and talk a bit more about these practical aspects of weak lensing. So you can see that as galaxy is beyond the spin-2 picture. And the key point here really is that as our surveys get more and more powerful, so that is as we gain statistical power, systematic effects will become more significant. So already, but even more so in the coming years, correct cosmological interpretation of observations will require a lot of astrophysics. But as a warm-up, let's start with a cartoon picture of how astronomers may see galaxies. So of course, galaxies come in different shapes and sizes and colors. And many of these properties are quite correlated. Now, 2 of the main properties that determine at least how an astronomer sees a galaxy is how many stars already exist and how many stars are forming right now. That then determines the balance between old and young stars in the galaxy. And with that, it's optical colors. So they're shown here in magenta for very UV-rich starburst galaxies. Then we have a main sequence there of blue galaxies or spirals, or sometimes also called late-type galaxies. Those are our typical disk galaxies, and many of these will have sufficient emission that we can detect them in upcoming surveys like Euclid or Roman. And I will explain that part of how we select these emission line galaxies later. And then if there's less star formation going on, eventually the hot and blue young stars turn off. And we're left with longer-lived stars that have reddish spectra. And we end up with red and dead galaxies. So those are our ellipticals, or originally named early-type galaxies. Since we will be doing quite a bit of spectroscopy, should also talk about how to, or what the key ingredients are for modeling a galaxy spectrum. And here I'll rely on a fantastic review on the spectral energy distribution of galaxies by Karthik Iyer that I had a lot of fun reading when preparing this talk. So as a function of rostrum wavelengths, you can just see here the flux density of a typical galaxy and the key components. So in blue, there is the stellar continuum, which may be the first thing that we think about, especially also in the cartoon picture of the previous slide, saying, well, galaxies are mostly made up of, or the luminous part of galaxies is primarily made up of stars. So that will give some continuum spectrum. Then in addition to that, there will be emission lines from the ISM, shown here in cyan, as the nebula emission. And highlighted already very helpfully is here H beta and oxygen 3, two of the typical emission lines that surveys use to select galaxies, say, for Euclid enrollment. Then, of course, in addition to stars, there is dust. And in general, I think the story of cosmology is that dust makes everything complicated. You can see here how dust in the spectrum attenuates the blue parts. And then there is re-emission in the infrared. Basically, that's the black body of the dust that gets heated by emitting, absorbing light over here. And then in addition to that, there can be some emission from AGN, which doesn't need to be our prime topic here today. So let's look at this in some more detail, just so that you understand how many assumptions go into modeling a galaxy spectrum. I think that is a useful thing to have a basic understanding for when you contrast that with the picture of galaxies that you get in Misha's lectures. Both are very useful, but at the end, I think we have to contrast them to understand what are the limitations of each. For example, if we thought that we really need to fully understand the stellar mass, star formation history, and stellar chemical enrichment of every galaxy to do cosmology, we wouldn't get very far. So that's definitely a point where we have to mostly switch to Misha's picture. But we should still be aware of what the key physics is going into this galaxy spectrum, so that we can later assess, do we have a complete galaxy sample? Could there be any kind of selection effects? So what you see here from blue to red is something called a simple stellar population. That is just basically a bunch of stars created at the same time, and then you let them age. So initially, there's quite a lot of blue and UV emission from short-lived massive stars. And then as the population ages, this blue and UV emission basically dies off. And you're left with these reddish spectra, include that, especially in galaxies that typically have a characteristic downturn at around 4,000 angstrom. Now, to get to more realistic spectra, we need a bunch of, in part, empirical ingredients. So we start out with a stellar mass function that just tells our initial mass function that tells us how the masses of stars are distributed when there is a burst of star formation. There, basically, you already have to decide whether this should be bottom heavy or whether there will be a lot of high mass stars produced. And then we need to understand something about stellar evolution. Seeing here in the space of surface temperature and luminosity, our standard Hasbro-Russell diagram, how long stars in different parts of this diagram live. And over here you have the young short-lived stars producing that UV emission. Down here, the low mass reddish stars. So understanding here what the isochrones there are and how long each of these types of stars live is another key ingredient. And then we need stellar spectra that tell us how stars in different parts of this diagram here look like in terms of their relative flux distribution. And at that point, you can then basically convolve all these things to get this single stellar population from the IMF, isochrones, and stellar spectra. Where at that point, it's also important to keep in mind that this SPS is not just a function of age, but also of metallicity. So it gets more complicated. And then finally, you can integrate this over the star formation history of a galaxy to get a composite spectrum. Now, I don't want to go into a class on ISM physics, though probably many cosmologists could use more understanding of the ISM. What I want to highlight here now just is that if we talk about emission line galaxies, then we really are probing the nebular emission from these galaxies. And that is, we are really sensitive to the local ISM conditions, chemical enrichment, winds, shocks, and outflows that all determine how these excitations happen, what the mean free path is, and so on. So there really is a lot of astrophysics that goes into baking an emission line galaxy. Let's get a bit more practical now, or even more astronomical, and talk about galaxy surveys. Now, the simplest thing one can do in terms of a survey is imaging. So we take pictures of the sky. At that point, we can, of course, measure the angular coordinates of any object, which may sound easy enough. Some of you may have done that in an astronomy lab course, even in undergrad. But in order to turn it into precision cosmology, one actually needs a detailed astrometric calibration for all these images. And we need to decide which of these objects are galaxies, which are stars. And both of those are actually already major research areas. So someone else could probably give a full set of 4 or more lectures just going into astrometric calibration and object detection. Basically realizing which of these pixels belong to an object, where's the centroid, all that's needed to get these angular coordinates. Clearly, as a next step, even cosmologists then need to decide what's a galaxy, what's a star, and we need some kind of distance estimate. Now, to separate galaxies from stars, what helps is that stars are point sources while galaxies are extended. So any fuzzy blob will certainly be a galaxy, but as the seeing gets worse, this task gets more and more tricky. So at that point, we need more information. And that's in part why most of these surveys take images of the sky, not just telescope pointing directly, but through different optical filters. And the transmission curves of typical filters here are shown in for the green filter, the red filter, and the so-called infrared filter that extends up to about 850 nanometers, so more optical to infrared. And then the different black lines, they show how an elliptical galaxy, so a galaxy spectrum that's dominated by old stars, gets redshifted. And for the redshift zero galaxy, you can see here this characteristic drop in the spectrum at around 4,000 angstrom, which is the feature we use to identify elliptical galaxies. And then as that galaxy gets redshifted to redshift 0.5 and 0.9, this break moves across the different filter. So one thing you can see here already is that if we only have these 3 filters, estimating redshifts based on photometry gets difficult for elliptical galaxies past redshift 0.9 or so. So we need even more information. And that's in part why a lot of these future surveys, like LSS and Euclid, include information more and more towards the infrared. So in addition of the GRI filters that I just showed you, LSS will also include the Z band, extending here to well over to around 9,000 angstrom. And Euclid, it's one of the space-based telescopes where the atmosphere doesn't prevent one from going to infrared, then extends even further into Y, J, and H band, going beyond, just slightly beyond 2 micrometers. This part here would not be accessible from the ground because of the atmosphere, but it's really essential for detecting high redshift galaxies that would otherwise just be redshifted out of the optical window. And of course, the more filters we have, the better we can estimate redshifts from photometry, because we can better differentiate between elliptical and spiral galaxies and avoid these kinds of mismatches. So that's how we would get to pseudo 3D galaxy coordinates from imaging data. If we want to be more precise in terms of separation between 2 galaxies and get a really good 3D map, then we need to take spectra of these galaxies. Or the classic approach to that would be to take a telescope that has a spectrograph and point that to individual galaxies. Of course, that's very slow going, and that's why initial galaxy redshift surveys had a few thousand galaxies in these surveys. Since then, technology has vastly improved, and nowadays, wide field galaxy surveys use multi-object spectrographs, say the recent BOSS survey or DESI, that use thousands of fibers. So in terms of having a telescope over here and galaxy light coming in, being reflected in the primary mirror, it then goes goes through the optical system and onto the focal plate over here. Which is amplified here. I will move to the blackboard soon, but this part really would not be fun drawing. They really want everyone to stay at the blackboard, right? Yeah. Great. But I'm glad to briefly catch my breath. Hmm? Okay. So then in the spectral, here in the focal plate, basically there are fiber cables connecting these different locations in the focal plane to the spectrograph. So going over here and then being split up into 3 different channels. And the important thing is that that allows us now to take spectra of many different galaxies at the same time. For BOSS, these focal plates were still drilled and connected by hand for each pointing. While in DESI, these 5,000 fibers are now automatically placed by robots, vastly increasing the efficiency. Now, of course, that's great, but we still need to know where to put these fibers. We can't just do that for all locations continuously on the sky. So that means we have to first select our targets for follow-up and for placing these fibers. And that is typically done from imaging data. To get the DESI survey going, there was the legacy imaging survey, consisted of 6 years of imaging with multiple telescopes covering about a third of the sky. And here's an example graph of what this legacy survey data looks like. It says typically illuminating magnitude around 25 over 1/3 of the sky. So in that, there's about 1.5 billion galaxies detected. And at that point, we really have to choose what to do next. Because DESI can take about 5,000 spectra at a time. That's a lot. But still, if we think that a typical night has a of order 8 hours, and we do 2 pointings per hour, that would be of order 64,000 spectra per night. And if we then give DESI 5 years, that would end up around 60 million galaxies or 60 million fiber placements. If all of these were unique, which they aren't, that would still mean that we can target, in the most optimistic case, only 4% of the galaxies from this imaging survey. So clearly, we have some more research to do and figure out really how to optimize our galaxy sample for spectroscopic follow-up. And the first goal here, of course, is that we want to have sufficient sampling density that we can measure power spectra, and in particular, the BEO feature. So that means we need a certain number density of galaxies so that the power spectrum at K of order 0.1 is not dominated by shot noise. And that tells us we need of order 10 to the -3 to 10 to the -4 galaxies per megaparsec cubed. And then, of course, another important goal is that we want each spectrum that we take to have sufficient signal to noise to get a reliable redshift during exposure time, which is preset. So that typically means that we end up with some kind of magnitude cut. And then, very important, we don't just want any random galaxies, but we want to understand what kind of sample do we have, what's the selection function. So that we can really assess completeness and all kinds of selection effects of galaxies moving in and out of sample. So in order to be able to characterize our selection function well, that means that we will end up with different galaxy types at different redshifts, and these are identified by color cuts. So typically, you might then hear about larger galaxies, emission line galaxies, and QSOs at even higher redshift. And I will take you through what this approximately looks like in a few diagrams. So here you now have color and color magnitude diagrams. Very typical tool of astronomers. This uses the bands from the legacy imaging survey, plus the infrared W1 band from WISE. And for example, when we talk about LRGs, then in this two color diagram, we have this nice separation of LRGs, color-coded here by redshift, compared to stars that can be quite well separated by imposing a cut like this red line. Then another important cut is some kind of luminosity cut that is implemented here in this color magnitude diagram. So that basically ensures that there will be sufficient signal to noise and that we can get a spectrum where we do see sufficient features to get a redshift within the pre-selected exposure time. Of course, this luminosity cut then also sets the overall abundance. So that's closely related to the number density that we need to achieve. And that's a very interconnected optimization. For emission line galaxies, these will accompany us through the redshift range of 0.6 to 1.6, which is the redshift range where we best understand their selection function. So here is another color diagram, this time for emission line galaxies color-coded by redshift, by photometric redshift from HSC and other photometry. So dark blue here is emission line galaxies below redshift 0.6. Dark red is above redshift 1.6. Now, the first cut that is easy to explain is that we'll have a cut in R minus Z color here. And that is implemented so that we easily reject ELGs at redshift above 1.6. Because at that point, the key emission line is outside the spectral range covered by the Delzy spectrograph. So that probably makes a lot of sense. And then a bit hard to see here, but there is also a black contour in here. That is the stellar locus, which is also shown over here, now in this G minus R versus R minus Z color space. So in order to now separate stars from particular low redshift galaxies, we also need to implement a cut over here. And then these green and red tracks, those show you typically evolutionary tracks of ELGs that are formed in a massive starburst at redshift 3 and then evolve. And for different scenarios, these two dots here show you where the galaxy ends up by redshift 1.1 in this color space. And then depending on the formation or the star formation scenario, these two cuts end up rejecting the corresponding low redshift galaxies. All right. Of course, this again is probably multiple, yes? I am not sure. So, I mean, you're talking about this one here, right? Yeah. I don't remember right now. Given how perfect the correlation is, that's probably some kind of artifact, I would think, but I can't tell for sure. There's a lot of facts to remember in these papers. Yeah. So this will become a bit clearer later on when we also talk about how to model the cosmological signal from these galaxies. But typically, any of these galaxy populations will basically cover some kind of mass, halo mass range. And in order to really interpret, especially the small scale clustering, we need to be able to characterize the halo mass distribution of these galaxies. And we also need to understand at what point, say, the least luminous galaxies or such are dropping out of our sample, because otherwise we can't translate number densities to cosmological evolution. Now that was a classic spectroscopy as a practice in a very modern level now by DESI, and similarly soon also by PFS on the Subaru telescope. But there is also a different approach, and that is slitter spectroscopy using a GRISM. So the idea here is that we do away with the target selection and instead take simplified spectra of all sufficiently bright galaxies within the field of view. So a GRISM is a combination of a grating and a prism. And that means that if you have the grating only, one wavelength will pass straight through, and the other wavelengths are dispersed and don't hit your CCD. So at that point, you get an image, a simple standard image of all the objects in the field of view at that central wavelength. Now then, when you switch from grating only to GRISM mode and put in a prism here, then the spectrum gets redirected. And that basically means that we disperse the spectrum along one dimension of the image. So you get a rainbow corresponding to the continuous blackbody radiation, and separated images of your object corresponding to distinct emission lines. in practice, this looks kind of like this. So each of the long streaks here is an object that is a discrete object that gets dispersed by the Euclid prism. And then the analyst's task is to extract the spectra and deal with potentially overlapping spectra in this kind of data. Unfortunately, I'm not a part of Euclid, so I don't know how it's going. But you can probably tell from this picture already that that is quite some advanced data analysis task. You now have the benefit of getting this kind of dispersion for all sufficiently bright galaxies. But instead of spending years doing the imaging beforehand, you now may spend a lot more analysis time extracting the spectra. And typically you will then have to find a joint solution for multiple galaxies where these spectrograms overlap. But it can be done. People have already done quite a bit of interesting science, for example, using the GRISM on HST. So at least for more isolated objects with less overlap, this is common practice in astronomy already. But Euclid and Roman are taking it to a new level in terms of the number of galaxies for which they have to extract spectra and the amount of crowding. Now, when I say that we will, in this case, disperse all sufficiently bright galaxies within the field of view, clearly, of course, to get a distinct feature in the spectrogram here, we need to rely on emission lines. And that then again limits the redshift range that a survey can cover. So here I'm very simply showing the observed wavelengths versus galaxy redshift for the three most standard emission lines, H alpha, oxygen 2, and Lyman alpha. And then as the dotted lines here, also some emission lines associated with AGN activity. So those will result in a much sparser sample, but can also be of practical interest. And you can see here in the gray box, that is the spectral range of the DESI spectrographs. So that tells you then where the different features move out of the redshift coverage of DESI. And for Euclid in particular, this means where the blue and red GRISM, which is what they're called, are both in the infrared. We really start getting meaningful numbers of galaxies basically when the oxygen 2 line moves into the blue GRISM. So it's about redshift 0.6, 0.7, and extends to redshift, say, 2.5. And then at much higher redshifts again, they start to pick up some more galaxies when Lyman alpha moves into the GRISM. But because of the huge distance of these galaxies, most of them will be very, very faint. And the number density will be much lower. So that's some practical facts of how we observe galaxies. I think the main thing I want to take you away from this discussion is that we will basically, in no practical setup, get spectra for all objects on the sky. There's either some target selection going on beforehand, or we have to rely on these emission lines within some GRISM with limited spectral coverage to basically extract spectrograms for ELG type samples over a limited redshift range. And then, of course, in the end, we want to do cosmology with this and connect this in particular also to the type of modeling that you're hearing from Misha. So while you're becoming experts already in the evaluation of small density perturbations, and I think tomorrow morning we'll relate that to the large-scale distribution of galaxies. I'll take a complementary approach here and focus on the highly nonlinear regime and talk through how at the end we can connect that to galaxy formation. So that will proceed in a few stages. First, we have to derive how halos form and what their clustering properties are. That is, we will go through gravitational collapse and then derive the abundance and biasing of halos in the peak background split. And armed with that, we can then calculate the nonlinear clustering of matter into the highly nonlinear regime using the halo model. And in order to connect that now to galaxy observations, we need to include basically all of astrophysics. And we'll do that in a cartoon picture that is, again, in slides after we've gone through the derivations for halos more rigorously. All right, so let's start out with gravitational collapse of halos, which is probably something that many of you have seen before, but let's just put it all together that we have some key facts about halos here. So let's assume we have some spherical top hat perturbation. And to do this on the blackboard, we have to assume that that is embedded in an otherwise completely homogeneous Einstein-de Sitter background. So the key equations governing the evolution then is mass conservation. And of course, because this evolves under gravity, we also have the equation of motion for a given shell. That's just gravitational attraction. And if we were not in Einstein-de Sitter, but in a different cosmology, there would be some other terms here. And at that point, we have to solve spherical collapse numerically. That's entirely possible. But for simplicity, we will do Einstein-de Sitter here and compare to simulations afterwards to see how amazingly successful this picture is. Now, the good news is that allows us to do this easily in class is that within Einstein-de Sitter, there's a parametric solution. And that is now just as a function of our parameter. One can verify that these two functions with the additional constraint that, or with the additional relation between the two coefficients satisfy these two equations. Now, with our prescription, with our solution for the evolution of time and radius as a function of our parameter theta, we can already picture what it looks like. And that is, we will start out here at theta of 0, with t and r being 0, and then go into some phase of expansion. Eventually, the system reaches a maximum point here at r max, t max, and then contracts, collapsing into a point here at 2t max. That looks nice, but let's understand a bit more what's going on and that it actually makes sense. So to really see what's happening now with our halo, we can start by studying the limiting behavior of the solution, which at times means, of course, a Taylor expansion. So at that point, we can just get a prediction for the evolution of the radius within linear theory. And for that, I just Taylor expanded T and R in terms of theta and did some algebra. All right, the first useful thing that we can read off here is that now using the relation between A and B, we can write this as so with that we see that to zeroth order our radius of the perturbation is just expanding as the background in Einstein de Sitter. So that's a very useful limiting behavior to recover. And then of course, also we can see that here, again, the perturbation, so it evolves with the scale factor, which means with the growth factor. So our linear radius here, or our linear approximation for the evolution of the radius, also, sorry, no, not yet. The next thing we need to calculate, of course, to really make sure that everything makes sense is the evolution of the density contrast extrapolated in linear theory. And that is just the density that we would calculate within linear theory divided by the background evolution in Einstein de Sitter. So at that point, of course, because mass is conserved, we use our expression here for our lin, plug in the constants, and find that our linear density contrast at the end is given by to leading order. Which is again proportional to the growth factor of the growth factor. So the density in linear theory at early times, this density contrast then evolves with the growth factor. That's useful to really now understand what's happening our halo in total. Of course, we also need to evaluate the real density, not just the linear extrapolation. And that is, we also need to evaluate the full nonlinear delta. That is rho of t over rho EDS of t. And for that, we start out again just with our standard expressions there for R and T. And to make it all a bit shorter for you, let me just give you the result. It's just a bunch of algebra, but that now allows us to evaluate both delta lin and delta at interesting times. So we can look at this at turnaround. That is T equals T max or theta equals pi, and at collapse. Now for the linear density contrast, we can now simply evaluate our expression here. And of course, we can also there just note by comparing our parametric expression for T to this curve over there, that B is just T max over pi. So let's just rewrite this here as 8 pi T, 6 pi T over T max, so we can evaluate more easily. And with that, we find that at turnaround, the linear extrapolated density contrast is just one of order 1.062 at collapse. Now plugging in 2 T max. This will have the important number of 1.686. So meaning that we expect a density perturbation that reaches an overdensity of 1.686 within linear theory to collapse into a halo. We can evaluate the fully nonlinear density contrast easily using the parametric solution at turnaround. Just plugging in theta equals pi. And I forgot to evaluate that when I wrote my notes. Sorry, I think that's of order 4.5 or so. I don't remember off the top of my head right now. And the big question, of course, is so what's really happening in terms of the density contrast of our halo at collapse? We don't just want to know what the linearly extrapolated density contrast is, but what's really going on in our halo. You can quickly notice that evaluating this within the parametric solution does not work. That gives infinity, because in this perfect picture, it would all collapse into a point, which is not what happens in practice. So in order to make progress here, we need to leave our parametric solution and think about what happens as this halo undergoes shell crossing and virialization. So at this time, we can simply say that the, of course, total energy should be conserved. That's our potential energy at turnaround. And that's and the total energy at virialization. And now using Virial theorem, that's just half the potential energy at virialization. And from that, we can then conclude that the virial radius has to be half the turnaround radius. All right, with that, we can now make progress to evaluating the actual density contrast here. Because we then know that the actual density will have increased by a factor of 8 compared to a turnaround time, simply because the radius decreases by a factor of 2. So that means we will have 8 times 9 pi squared. And because we go from T max to 2 T max, our EDS background also evolves. And in particular, that then means that this factor of 2 in the background evolution will then correspond to a factor of 4 in the change in the EDS density. So at that point, we end up with 18 pi squared minus 1. And that's of order 200. Not quite exactly, but that is then the actual overdensity in our halo once it has collapsed and undergone realization. That's a useful number to keep in mind. Both this 200 and that in linear theory, we would need to reach this linearly extrapolated density threshold of 1.668. With that, we have a picture of how halos form. That's nice, but we can't really calculate much with it. So we need a few more ingredients. That is to really start to talk about the halo model and clustering of matter. We need a prescription for the distribution of halo masses and the biasing relative to the matter fluctuations. And then we're in business. And for that, I will take you through the nice toy model of Krause and Schechter from 1974, which is amazingly useful. And the basic idea here is that we want to compute the volume in regions of space where the linear density contrast exceeds this critical number of 1.686 as a function of smoothing scale. So when I say smoothing scale here, we want to consider really the region that will collapse into a halo of mass m. So and then we calculate the corresponding variance of the density field smoothed on this scale R of m. Now that is something that is obvious how to do based on Mishra's lectures, but let me write it out again so that you see exactly how the mass and redshift dependence factorizes here. So again, I have my smooth my power spectrum times the window function now with exactly that radius of corresponding to mass m, and we can just evaluate that here just at redshift 0 or alternatively in comoving coordinates, and then to get the redshift evolution in, that is just a growth factor squared. Sorry. So with that, we have a convention how to where to exactly factorize this out here, and can just use the mean density at redshift 0 here. And then we can, and now realizing that the density field is a Gaussian random field, we easily calculate the fraction of space collapsed into halos above some mass. And I forgot to write this clearly here. Sorry. We call this number here delta C, the critical density contrast. So basically, we will now want to integrate over all regions that have exceeded this critical density contrast. And then using the PDF of our Gaussian density field. Okay, I hope the structure of this equation makes sense. There's just one problem. When we integrate this out and go to small masses, you would find that only half of all space collapses into halos. That is a shortcoming of this picture, which at that point Krause and Schechter fixed by putting in basically a fudge factor of 2, which then ensures the correct normalization. And at that point, we can write the final result as this factor 2 times the error function. So that's now a nice compact expression where we have defined the peak height nu. Well, that is you can see is our collapse threshold in units of the variance of the RMS of the density field at that given smoothing scale. And you will later see in a plot how well this works despite the fudge factor of 2 and being a fairly simplified calculation. If you want to go beyond that, there's a beautiful paper from Dick Bond from 1999 on extended Krause factor, where he considers different trajectories to undergo collapse and rigorously derives this factor 2, but we're not going to do that here. Now our remaining work is easy. We just have to go from this fraction of space that's collapsed above a certain mass to now our number density of halos. So in the end, we want something like rather than something cumulative above a mass threshold. So of course, that means that we will need a differential of our collapse fraction above a given mass and redshift with respect to mass. And then we still need to turn this fraction of space into an actual number of halos. That means we still need a conversion factor to go from space fraction to number of halos. And we can slightly rewrite this again to make it useful for the calculations that follow. So we first take the derivative of our collapse fraction with respect to nu, get a factor of delta C in there that cancels out with the prefactor. And this quantity here with a little bit of algebra, you can show that that's, again, just a very simple expression. And with that, we have a very compact expression for our halo mass function. Am I missing a factor? I just saw someone raising an eyebrow. And I feel really slow today. Sorry. But that is definitely the structure of the expressions. And I've also written it out here earlier. So yes, I think that's okay. So we now have our nice compact prescription for the halo mass function, where one thing that we can directly see is that there's an exponential cutoff at high masses. So basically, whenever sigma at a given mass equals delta C, then we enter this cutoff regime here now. And today that would be at about 10 to the 13 solar masses. So objects above a halo mass of 10 to the 13 are exceedingly rare. And here is a nice also visualization of more modern mass functions, which basically take the route of making this f nu, that is just basically nu e to the minus nu squared over 2 in Press-Schechter into some parametric form, and then fitting those parameters to simulations. Here's one example from n-body simulations in different cosmologies and different redshifts, developing some fitting function. And yet another paper also showing the comparison of this fitting function over here to different analytic approaches, showing how in spherical collapse in general, there's a bit of this mismatch in shape between the very simplest spherical collapse predictions and the actual measurements that can be further improved by considering not just a spherical collapse, but ellipsoidal collapse where different parts of the halo start collapsing at different times. Or one can just go the route of a fitting function. But still, the main point is that this toy model of a spherical collapse gives us some pretty nice idea for the overall behavior abundance of halos as a function of mass. And I'm sorry, I briefly need to sit down. As you can probably guess, the next step then still is that we need to take one step further and calculate the biasing of these halos. So let me just start with a sketch while I sit. No, this is too low. But what we're going to do next is the peak background split. Let's just consider some slice of space and the linear density contrast, where it's somewhere we have our critical density contrast delta, saying that any fluctuation that exceeds it will collapse into a halo. And furthermore now, we will decompose our density fluctuation to some kind of long range mode and small scale fluctuations imposed on top. That means now that we will form halos here, here, and the big one over here. We can clearly see now that, of course, this large-scale density fluctuation modulates, in that sense, the small-scale fluctuations and really changes where halos will form. So the idea now is that we want to modify the spherical collapse that we did before to incorporate the large-scale matter fluctuation. So that is, we want to basically decompose, and let's call this here the large-scale mode. So we want to decompose our matter fluctuation into a large-scale mode plus small-scale matter fluctuations. And that then basically means that we can write an effective now threshold for collapse. That is a delta C minus delta L, modulating this barrier. And at the end of that process, we want to calculate how the halo density relates to the large scale meta density. So that at that point, then again, is a bias definition similar to what you will hear from Misha, that is relating halo density to the large scale meta fluctuation. Let's do this. So going back to our mass function from over there, we now want to calculate first of all the halo mass function in the presence of this large scale mode. That is really just plugging in there on the other side. Now we can, of course, again, Taylor expand, where the first term at that point, of course, is just our regular halo mass function in the absence of a large scale mode. And then expanding our projector function a little f here. We get a logarithmic derivative because we factored one out. Simplicity first, taking the derivative with respect to nu. And then we get factor of 1 over sigma from the coordinate change times delta L. And we evaluate that again at our standard barrier. So that's standard delta C over sigma mz without the modulation of the large scale mode. Now, the only step we still need to do then is to calculate our halo density contrast to first order, of course, at the given position. And that is at that point, of course, again, just the relative overdensity. So we have Bn, Bm given some large scale mode at that location compared to the homogeneous one in the absence of a large scale mode. And of course, at that point, dividing out this term makes it easy. We're basically left with what's over here. And we can then also just explicitly take that new derivative of the function over here. Let's do that one step later. And with that, we then have an expression for the linear bias infrastructure theory. Again, the real measure at the end is how does it compare to simulations. Well, we have another nice comparison from a large suite of different box sizes at different redshifts for an overdensity of 200, comparing the measurements from simulations to spherical collapse, as shown by the black dotted line here. So clearly, again, it is useful to make improvements to this simple expression for galaxy bias and devise more complicated fitting functions. But as like for a quick blackboard exercise and to get some insight on halo formation, this is doing pretty well. All right. Now back from halos to gastrophysics. Here we had this nice picture of just a simple spherical collapse and calculating the abundance and spatial distribution of halos in that picture. Of course, in reality, it's more complicated. In part, of course, because yes, at a given time, regions above that have just reached this critical density threshold will collapse. But in practice, of course, this may proceed through a more complicated process with high overdensities collapsing first, and then individual halos also merging into each other. So in simulations, for example, one can then extract merger trees, showing here how a halo is observed at the final time has actually merged together from many different progenitor halos that existed at earlier times, and that of course collapsed because they reached the corresponding critical overdensity at earlier times. And of course, when we now talk about how galaxies evolve, this will become a lot more important. So when I showed you the mass function halo bias in simulations, you could easily see how the different colors, that means halos at different redshifts, lined up very nicely for these predictions. But for galaxies, that story will change a bit. So that means now we will have to follow these halo merger trees and understand what happens to a gas. That is by now a pretty classic story in astronomy. We've just calculated step one here, that is how structure formation is driven by gravitational instability. In a slightly longer summer school, we could then also calculate how dark matter protohalos get spin due to tidal torquing, which is a fun calculation, but not in 4 lectures. And then the next step described already by Hoyle in 1949 is how galaxies form inside these dark matter halos in a 2-stage process. That is, after the dark matter halo has formed, there is the fall in of baryons, where they get shock heated, described in more detail in papers in the late 70s. And gas then cools primarily by radiative transitions, so that the typical mass of a galaxy is set by cooling arguments. And then to really go through the formation of disk galaxies, we have to follow the cooling of gas onto the dark matter halo centers and consider conservation of angular momentum, so that we can calculate why disk galaxies rotate much more quickly than their supporting halos. And again, most of this had been laid out in principle in the late 70s, early 80s. A bit later then came the detailed understanding how elliptical galaxies form via mergers of disk galaxies. So at that point, making clear that the classical labeling of early and late type galaxies was just the wrong way around. And the step from halos to galaxies is really where a bunch of astrophysics will come in. If we did the simplest possible comparison, that is between the halo mass function, rescaled here a bit, assuming some kind of mass to light ratio compared to the abundance of groups in a galaxy redshift survey, as a function of luminosity. We can see that these two functions have different shapes. In particular, you clearly see that the galaxy luminosity function here turns off even more sharply at the high mass end than the halo mass function. So something must be happening there that really changes the mass to light ratio. And similarly, also if we match there at the knee, then the mass light ratio is also off at the low mass end. And that's really where baryonic physics has to come in, so that we understand how to go from the halo mass function to the galaxy luminosity function. So here we will follow the gas. We start out with a dark matter halo, and baryons fall in, are shock heated, and start cooling. And this cooling process then will proceed out to larger and larger radii with time. And we will talk through some of the key ingredients here and just understand the approximate scaling of the relative time scales. Again, a lot of this is just some energy reservoir divided by some rate to get a time. So I decided I would much rather do this on slides, showing you the huge astrophysical uncertainties in the various ingredients than doing the basic dimensional ratios on the board. Now, when we say that baryons are shock heated to the halo temperature, let's briefly consider what the relevant temperature scales are here, because that then really determines what the relevant cooling mechanisms are. So we can probably say that our gas falls in from a large distance, where the potential of the halo is basically zero. That means that basically we can just relate the infall velocity to the potential of the halo at radius where the gas gets shock heated. And at that point, we can then convert this velocity, assuming hydrostatic equilibrium, into something that's called the virial temperature. And that's really just energy conservation in the infall plus virial theorem. So that we'll find that in a halo of order 10 to the 8 solar masses, gas already gets heated to a temperature of a few times 10 to the 4 Kelvin. That's quite hot. When you think in terms of potential hydrogen atoms. And then, of course, as we proceed to more massive halos, this rises steeply because we have a mass to the 2/3 dependence here. And the next step then, this hot halo gas cools, and that cool gas falls towards the center, where it can form stars and where it gets interesting for a purpose of luminosity functions. So again, here's a simple type of arguments that one then makes, saying, okay, we start out with this total kinetic energy over here and divide by the cooling rate. So just gas density squared times some cooling function. And that tells us how long a halo should take to cool. And at that point, we have to think about, well, what is our cooling function? What processes are at work? In small halos or in low mass halos, so with a virial temperature below about 10 to the 4, molecular cooling is most efficient. So here we use here basically collisions, then excite vibrational rotational energy levels in H2. At slightly higher halo masses, corresponding to very temperatures about 10 to the 4 to 10 to the 6, where gas is partly but not fully ionized, atomic cooling will be most efficient. And in cluster halos above temperatures of about 10 to the 7, Bremsstrahlung is the dominant cooling process. That is all just basically details of this our standard radiative cooling radiative processes class. But the interesting part now is again in terms of how huge uncertainties are in all these basic equations, how this changes with metallicity, and with that also with cosmic time. So here is this cooling function shown as a function of temperature, both for a primordial gas and then with increasing metallicity. We can clearly see how huge of a difference this makes in the regime of atomic cooling. So the estimates for the cooling time will vary substantially as our galaxies get more chemically enriched over time. Now, when we think about how this cooling radius then moves outward over time and where this is efficient, we can look at a few different important regimes. In particular, if our cooling time is larger than Hubble time, obviously cooling is not important. If the dynamic time is less than the cooling time and less than the Hubble time, we're in quasi-static equilibrium. And that means that our gas will contract slowly as it cools, but the system has sufficient time to contribute, to continue to reestablish hydrostatic equilibrium. So this is a fairly slow and steady process. On the other hand, if our cooling time is less than the dynamic time, then gas cannot respond fast enough to loss of pressure. And cooling basically proceeds faster and faster. And the gas falls to the center of the dynamic system on a free-fall time scale. Putting this into a diagram, here is a nice visualization in terms of temperature and density where cooling is effective. Now these lines over here show you basically lines of constant halo mass. And the horizontal lines correspond to the gas densities expected in our visualized halos between redshift 0 and redshift 5. That is simply a fact that that's simply due to the background evolution and the conversion of delta to proper densities. And then you can see in this space, depending on metallicity between primordial and solar metallicity, on which scales cooling is efficient. So clearly, going from primordial to solar metallicity means that halos of about group scale will cool much more efficiently, thanks to this strong change in cooling function. And you can see, of course, here that going from this curve to that curve, that is well over a decade in halo mass, where cooling is effective and we can form stars. So that's clearly a massive factor when we want to study galaxy evolution. Now, at late times in massive systems, above that group scale, cooling is typically smaller cooling radius is typically smaller than the Virial radius. And that means we, especially cluster systems, will form a quasi-static hot halo. And the gas from the central region cools and is accreted onto the center. So at that point, of course, one can then estimate an accretion rate and relate that to the star formation rate, which primarily just depends on how our cooling radius moves outward. So this intimately depends on the cooling function. And at that point, when we're forming stars, we're ready to get to the really interesting, or some might say ugly, gastrophysics of star formation and feedback. But I think I'm at 1.5 hours now, right? I should probably stop here and do that next time. So we will get to feedback next time. And I'll stop here for questions. Yeah.
Starting from the other function, we do abandon them, to the domain of the gas. And using the relative gas function and
yeah.
Gas in that form.
Yeah.
Maximum the number density.
Yeah.
In some form, I see instead that the galaxy function to the integral of the number density of arrow of the time mass, so not weight of the letting the arrow of another function. I was wondering why. What's the difference? Why do you have no?
I'm not sure I fully understand the setup right now. So, I mean, one can always define an empirical matching. That is just a mapping from one to the other. But this means at that point, you will need a changing mass to light ratio. As you go to as a function of luminosity or halo mass. And of course, that is then implicitly defined from this explicit abundance matching, but without any physical explanation. In the plot that I was showing here, I was just going the opposite way of assuming constant mass to light ratio, just to show that there needs to be additional physics regulating star formation at both the low mass and high mass end. Hmm? Yeah. It will get more fun. So most of the models that actually go through this process that I described here are then so-called semi-analytic models, which means that they start out with merger trees generated from simulations or extended projector, and then just follow the gas within those halos. Mm-hmm.
And then like after, like the redshift appeared.
Yeah.
I guess that I'm wondering why. I guess at some point we about the Halloween expansion. There's kind of redshift event there, or what's the reason why? You need to go back exactly there. Mm-hmm. You see, like first line you have no redshift, and then it appears that it's that.
Yes, that primarily comes from the conversion of the circular velocity to halo mass. That is an evolving function of redshift. Mm-hmm. Sorry, I don't see it right now. This one? That's the halo density. Yes. Hmm? Yes. Number density over number density. So to go from abundance to density contrast. But just ask if you found a problem that you're looking at it. Okay.